Welcome to Complexity Made Simple, and my name is Paul Allen. And before we get into today's fantastic video newsletter, what I'd like to talk to you about is all the materials that you can purchase to help to support the channel. We've got these fantastic textbooks that range from the simple statistical process control for small batch production. We've got the 7 quality tools for world-class problem solving, which is essentially yellow belt material. Then we move on to design of experiments for 21st century engineers. Every engineer and scientist needs to be able to do design of experiments. And then finally, drink tea and read the paper. The most fantastic green belt handbook you can buy on the market today, full of practical tips and fantastic physics that'll help you become a world-class engineer and a world-class quality engineer. Of course, you can also click on the link to buy me a coffee and make a donation. That would be fantastic. But at the very least, click on subscribe, click on like the video, because it all helps to support the channel. Many thanks for your help, and now on to today's video. Welcome to Complexity Made Simple, and in this video newsletter, what we're going to talk about is a statistical tool called hypothesis testing, and why, as an engineer, you need to understand and use hypothesis testing. So that's what we're going to be looking at. We're going to introduce the idea of a hypothesis test. Now, if you didn't know, all of science is based on conducting hypothesis tests. So anytime someone has an idea about how to change or improve a process, they are going to use a hypothesis test. Research scientists are doing this every single day of the year. Now, as an engineer, what will you potentially be doing? You will potentially be making a deliberate process change. So that's where you would be using this. You're making a deliberate process change. So what you're saying is, I've got an idea. I'd like to change my supplier. I think it would be better. I've got an idea. I think I'll run the process faster. I think I'll run the process hotter, etc. You're making a deliberate process change. So you're collecting evidence before you made the change. You're collecting evidence after you made the change, and then you're running one of these. Now, okay, why do I need some kind of mathematical test, and what is this thing? Well, it goes like this, look. Imagine we had a bucket of parts in front of us. So we got a big bucket, maybe there's 10,000, 20,000 pieces in the bucket. And imagine there is some feature, let's say it's the hardness of those parts that interests us. And in order to check that we've made these 20,000 pieces correctly, what are we going to do? We're going to sample them. Now bear in mind, this is obviously a static process. These parts have just been produced off a machine. So the process isn't moving around, it is a fixed population. Bear that in mind. It is a fixed, unmoving population. Now what you're going to do is sample. So you take 30 pieces, you measure the 30 pieces. What do you get? You will get a distribution for those 30 pieces. You will achieve an average. You will get a standard deviation. But let's say you don't trust your first sample, so you decide to sample again out of the same bucket. So now we take a second sample. What do we get? we get a distribution with a mean and a standard deviation. Now this is a static process, it's not moving. But here's the question, what's the chance that these two are identical? And don't forget, what they were supposed to represent was what was in the bucket. So whatever's in the bucket, let's say what was in the bucket looks like this. These two are supposed to look like that. Now the first question is, what's the chance that these two are identical? Well, pretty much there's no chance that they're identical. You're looking at two estimates. Two estimates will always be different. And obviously, if you took a third sample, another 30, that would be different to these two. So look, a static process that isn't moving, the sample that you take won't stand still. It keeps moving. So you always see difference in two groups. But of course, you made a deliberate process change. So you took a sample out of the bucket, made a change, made a new bucket, and then looked at the second data set. And what you observed was a shift. But you were always going to observe a shift. Two groups will never be identical. Now, because of that, how do I know what I'm looking at was me? Maybe it was two groups. Now think about this from a scientific point of view. We're talking about sampling, but think about this from a scientific point of view. If I took two groups of cancer patients, two groups of 500, and I gave them the exact identical treatment, I treated them identically. When I looked at the survival rate for those two groups of people, would it be identical? No, of course it wouldn't. One would be better than the other. But they had an identical treatment. So when people get identical treatments, we get different results. How will we ever know when the results we're looking at make a genuine difference? Now that is what a hypothesis test is going to do for you. So the hypothesis test is going to tell you whether you're just looking at two lucky groups out of a fixed process that are just a little bit different, or the difference you're looking at is a genuine signal created by your deliberate change. Now think about it like this. Let's say we're sampling from a static process. Let's say the first person that goes in is having a very unlucky day at the office, and their distribution, which is supposed to represent this, all comes from one corner of the distribution. And let's say the second person that goes in, that's also trying to represent the blue distribution, they go in and they're having an unlucky day at the office, and their sample all comes from that corner of the distribution. Now ask yourself, is that possible? Of course it is possible, but the question is it likely? Is it likely that we're going to get two samples so far apart? Now, of course, what's another word for likely? Another word for likely is probable. Probability. So if we were clever enough, could we work out the probability of these two samples looking like this? Well, indeed we can. And that's what comes out of a hypothesis test, a probability value. And what the hypothesis test assumes is your deliberate change made no difference. And then it says, if that was the case, what's the probability your two results would end up so far apart. Now, this is your probability of being wrong if you conclude your change made a difference. So because it's your probability of being wrong, what do we want it to do? We want it to go and be very small. Now, typically when we say small, the number we're trying to get below is 5%, 0.05. So in other words, there is only a 5% chance my samples would be so far apart if my deliberate process change had not made that difference. You always get difference. Two samples will always shift. The question is, did you do it, or was it just a lucky day at the office? And if you don't use hypothesis testing, what do people always assume? They always assume they created the shift. Now ask yourself as an engineer, how many times have you thought you found the answer, only to try and repeat the test and the process won't behave itself? And that's because you think every shift was you, when actually it could have just been luck. Well, the p-value is going to tell you you couldn't be that lucky. There is only a 5% chance you're wrong if you conclude your new process setting made a difference. And if you don't use hypothesis testing, you will just learn nothing about your processes. As an engineer, as a research scientist, hypothesis testing is the most important tool you can use to get true process knowledge and drive your processes from control to excellence, to make more money and to smash the competition.